For this question, we have the function f of x equals 11 over x, and we're also told that it is a one-to-one function. We want to find the inverse of the function f, state the domain and range of f, state the domain and range of f inverse. So to find the inverse of f, I'm going to start by taking my function f of x equals 11 over x. And I like to do this in 3 steps. The first step is to change the notation of f of x to y. So we're going to write y equals 11 over x. The next thing that we're going to do is switch the x and y variables. So we'll write the equation x equals 11 over y. And then finally we're going to solve for y. Rewrite the equation so that we have y equals. Now this step right here is essential to creating the inverse. Inverses have the x's and y's switch, so by us switching the x and y in our equation, that's what creates the inverse. So I'm going to solve for y. We're going to solve for y by multiplying by y on both sides. So multiply by y on the left, multiply by y on the right. The y's cancel on the right, and we have 11 equals xy. And now I'll solve for y by dividing both sides by x, and we have x equals 11 over x. So the inverse of this function, the symbol that we use for inverse is f with a -1 in the superscript, is 11 over x. So this is quite interesting because the original function is 11 over x and the inverse is 11 over x. So we have a function that is the inverse of itself. Okay, if we're feeling a little bit iffy about that, we can verify. The way that we verify that two functions are inverses of each other is by doing the composition. So if we do the composition and we get x, then we have inverses of each other. So I'll substitute 11 over x into 11 over x. That would give 11 over 11 over x. This is the same thing as 11 divided by 11 over x. When we divide fractions, we multiply by the reciprocal, so that's 11 times x over 11. The 11's cancel, and we get x. Also, if we verify the other way, f inverse composed with f, we get the exact same calculation, giving us x. So these two functions are inverses of each other. Or stated more clearly, this function is an inverse of itself. So then we want to state the domain and range of each one of these functions. So f of x is equal to 11 over x. And because this is a rational function, we're looking for where the denominator is equal to 0. So the denominator will equal 0 when x is equal to 0. So we exclude that value from the domain. The domain of f is -infinity to 0, union with 0 to infinity. The domain of f inverse is the same function, 11 over x. So the domain of f inverse is -infinity to 0, union with 0 to infinity. And something I talked about earlier is that inverse functions switch the x and the y variables. Domain is the set of x values, range is the set of y values. So if we switch the x and y variables, we're also switching the domain and range. So the range of f is going to be the domain of f inverse, so negative infinity to 0, union with 0 to infinity. The range of f inverse is going to be the domain of f, negative infinity to 0, union with 0 to infinity. So we have this particular function, f of x equals 11 over x, has an inverse that is also 11 over x, and we have the domain and range of each function being all real numbers except for 0. The function g of x is equal to that's a 3x minus 8 over 7 minus x is 1 to 1. We have a 1 to 1 function. We want to find the inverse of g, state the domain and range of g, and state the domain and range of g inverse. So let's start by finding the inverse of g. There's a three-step process that we can go through to find the inverse. We have g of x equals 3x minus 8 over 7 minus x. And the first thing I'm going to do is change this g of x to y. Now the reason why I'm doing that is really just to make our symbols a little bit easier to work with. G of x is four different symbols there, y is just 1, so it's less for us to write. The next thing we're going to do is what is going to help us produce the inverse of g. With inverses, the x's and y's are switched, and so we're going to switch the location of our x's and y's in our equation. So we're going to have, instead of a y here, we're going to have an x, and then 3y minus 8 over 7 minus y. So this y became an x, these x's became a y. And the final step, which is going to take the longest, is to solve for y. So we want to rewrite this equation as y equals. So we need to solve for that y. So let's work on that. So this is looking a little bit messy at the moment because we have multiple y's in our equation and the y is in the denominator. So first I'm going to address the issue of the y in the denominator by clearing fractions. We're going to multiply both sides by 7 minus y. So on the left I have x, and I'm going to multiply that by 7 minus y. And on the right I have 3y minus 8 over 7 minus y, and I'll multiply that by 7 minus y. Now on the right, this clears the fractions, so it cancels out the fraction on the right, leaving me with 3y minus 8. And on the left, I'll use the distributive property, and that gives 7x minus xy. So now I've gotten rid of the y in the denominator, and now I need to fix the other issue of having multiple y's. So I want to collect all the y's to one side of the equation, and everything that is not a y, every term that doesn't have y, onto the other side. So I'm going to move this term over here so that all the y's are on the same side, and I'm going to move this term over here so that every term that doesn't have y is on the other side. So that will give negative xy minus 3y equals, Oh, I don't like how this is going with all these negatives, so I'm going to switch it up. So here's what I'm going to do. Instead, I'm going to move this term with y to the right, and I'll move this term that doesn't have y to the left. So all the y's will be on the right, and all the terms that don't have y will be on the left. So that will give 7x plus 8 equals 3y plus xy. So now that I have collected the y terms, I'm able to factor out the y. And when you factor it out, you now only have one y. Now I can solve for y, and I'll divide by 3 plus x on both sides. That gives y equals 7x plus 8 over 3 plus x. And now that we've solved for y, we now know the inverse. So our original function was g. Our inverse is g inverse of x. That's 7x plus 8 over 3 plus x. So we now know the inverse. I'm going to zoom back out so that we can see the other parts of our question. So the other parts of our question say, state the domain and range. So we want the domain and range of G and the domain and range of G inverse. Now we have some strategies from previous chapters for finding domain. So let's write down our two functions. We have g of x equal 3x minus 8 over 7 minus x, and we have g inverse of x equaling 7x plus 8 over 3 plus x. And we're looking for the domain of each one of these functions. They're both rational functions, so if I set the denominators equal to 0, I'm going to find the domain. So for the g, I'll set 7 minus x equals 0. Add x on both sides, that gives 7 equals x. So we know that 7 is a restricted value. It will cause the denominator to be 0 and the function to be undefined. So the domain will be all real numbers except for 7. So the domain of G will be negative infinity to 7, union with 7 to infinity. That's all real numbers except for 7. For G inverse, I'll set that denominator equal to 0, subtract 3, and get x equals negative 3. Negative 3 is our restricted value for G inverse. So its domain will be all real numbers except for negative 3. The domain of G inverse will be negative infinity to negative 3, union with negative 3 to infinity. So as we've said earlier, the x's and y's get switched. So the domain and range get switched. So now that I know the domain of both, I can know the range of both. The range of G is the domain of G inverse. So that's negative infinity to negative 3, union with negative 3 to infinity. The range of G inverse is negative infinity to 7, union with 7 to infinity. So our strategy for finding the range is that we use the domain of the inverse. So we now have our inverse function, which is right here, 7x plus 8 over 3 plus x, and we have the domain and range of G and the domain and range of G inverse. In this question, we're given a graph of a function that we're going to call f. And we're asked a bunch of questions related to the inverse of this function. So the first question that we're asked is, what is the domain of f inverse? And what we know about inverse functions is that the x and the y value get switched. So really, if we're looking for the domain of f inverse, and we're given f, we're going to use the range of f to answer this question. So because x's and y's get switched, the domain and range get switched. So I'm going to use my ruler, and we're looking for the range of f. Those are the y values. So my lowest range range value or y value is -5. So my range of f starts at -5, and my highest range value or y value will be 6. So the range of f is -5 to 6, and that means that the domain of f inverse is also -5 to 6. So then we're asked to find, on the next part, what is the range of f inverse? So as we just said, the domain and range get switched, and the range of the inverse will be the same as the domain of f. So let me take my ruler, hold it vertically, and now we're going to be finding the x values, the domain of f. So that starts at -6. So my domain of f starts at -6 and continues all the way until 4. So we have a domain of f being from -6 to 4, which is the same thing as the range of f inverse. And the next thing that we're looking for is the y-intercept of the inverse. So typically when we're looking for a y-intercept, we let x equal 0. However, remember that our graph represents f, but we're really interested in the inverse. The x and the y get switched, so we really want to find when y is equal to 0. So y is equal to 0 right here. So just to clarify, on the graph of f, we have the ordered pair -2, 0, which is an x-intercept. With the inverse, the ordered pairs get switched. The x's become y's and the y's become x's, and that is a y-intercept of the inverse. So the y-intercept of f inverse will be at -2. So then let's take a look at the next part. This one says evaluate f inverse of 0. We want to find f inverse of 0. So on the inverse, our ordered pair would be 0, comma, and we don't know what that y part is. But on f, the x's and y's get switched, so we don't know the x part, but we know the y part being 0. So if I were to use more formal notation for what I'm doing here, if I'm looking for f inverse of 0, I know that f of something equals 0. So I'm looking for a y-coordinate of 0. And that's going to occur right here. This ordered pair has an x of 1 and a y of 0. So f of 1 equals 0. I'm sorry, I've stated that incorrectly, so let me correct myself. So that does not have a y-coordinate of 0, that has an x-coordinate of 0. So we're going back to this spot right here. This spot has y of 0 and an x of negative 2. So f of negative 2 equals 0. So you can see how easy it is to get confused on this. So you get f of negative 2 equals 0, and that is f inverse of 0 equals negative 2. So this one, the answer is negative 2. Okay, so let's try it again so we can get a little bit more clarity. So on the next one, we want to evaluate f inverse of negative 5. Okay, so let's do that over here. F inverse of negative 5. We're not sure what the answer is, but it's going to produce an ordered pair, negative 5 and something that we don't know. Let's leave it as a question mark. Now with f and its inverse, the x's and y's get switched. So with f, we'll have a question mark on the x part, but we'll know the y part to be negative 5. So on my graph of f here, I'm looking for a y value of negative 5. So right here we have a y-coordinate of negative 5 and an x-coordinate of negative 6. So we know that f of negative 6 is equal to negative 5, and f inverse of negative 5 is negative 6. So the answer to this one would be negative 6. So then we have our next part, f inverse of 6. Let's do it in a different color because my work is getting a little jumbled here. We're finding f inverse of 6. We don't know the answer. So for the inverse, we would have the ordered pair 6, comma, something we don't know. But for f, it would be f of that number we don't know equals 6. So we're looking for a y-coordinate of 6. Right here is a y-coordinate of 6. That ordered pair is 4, 6. So we know that f of 4 equals 6 and f inverse of 6 equals 4. So we get an answer of 4 for part F. F inverse of 6 equals 4. Okay, so let's do the last one. We'll do it in green. So we have f inverse of 1 equals something we don't know. That would give an ordered pair 1 question mark. F of that question mark should equal 1. So that 1 becomes the y-coordinate. So having a y-coordinate of 1 will be right here, and that ordered pair is 0, 1. So f of 0 equals 1, f inverse of 1 equals 0. So f inverse of 1 equals 0. So let me zoom out so we can see all those parts. And the main thing to keep in mind is that with inverses, the x's and y's get switched, the domain and range get switched. From this question, we're given the function f of x equals negative x plus 1 squared minus 1. This is a quadratic function in vertex form. And it's in vertex form because it's fitting this format here, a times x minus h squared plus k. Now, there are three things that I'd like to know about this particular quadratic function. The first thing I want to know is what is the vertex? So in order to know the vertex, you have to know that this hk represents the coordinates of the vertex. So the ordered pair hk is the vertex. We can match those positions up in our problem. And the only thing is that you notice you have a minus sign in the vertex formula, but we don't have a minus sign in our equation. Now, every addition can be written as subtraction if you subtract the opposite. So you turn that plus into a double negative, and that's going to make our x-coordinate a negative. So we have a vertex of negative 1, negative 1 for this problem. The next thing I want to know is does the graph of this open up or down? Now, the graph of a quadratic function will be a parabola that either opens up or down. And we can determine if it opens up or down based on the value of a. Anytime a is positive, the parabola will open up, and anytime a is negative, it will open down. You can see that our value of a is negative 1, and so since a is negative 1, which is negative, we know that the parabola opens down. And the final thing that I want to know about this function is the axis of symmetry. Now, as I said a moment ago, the graph of a quadratic is a parabola, and these parabolas will be symmetric around the vertex. So let me mark where the vertex is. And if we draw a vertical line going through the vertex, what you'll see is a mirror on either side of that vertical line. You'll see a mirror image on either side. And so we call that vertical line the axis of symmetry because on either side of that line it creates that symmetry or that mirror. So we're going to be able to find the axis of symmetry using the vertex, and since it's a vertical line, we're going to use the x-coordinate of the vertex. And we have the axis of symmetry being the vertical line x equals negative 1. For this question, we're given a quadratic function f of x equals negative 1/4 x minus 1 squared plus 3. This is a quadratic function in vertex form. And it says address the following. Well, the following is that we want to find the x-intercepts and the y-intercepts of this quadratic function. So we're going to start with the y-intercepts. They tend to be a little bit easier to find. So to find a y-intercept, we're going to let x equal 0. So substituting a 0 into the function, we get negative 1/4 times 0 minus 1 squared plus 3. We're going to follow order of operations to simplify here. 0 minus 1 is negative 1. We're going to complete the exponents. So negative 1 squared is 1. 1 times negative 1/4 is negative 1/4 plus 3. So we need to get a common denominator to add these together. So I have a denominator of 4 on the first fraction, so I'm going to multiply by 4 over 4, so I have a denominator of 4 on the second one. That would give me 12 over 4. Add those together, and we have positive 11 over 4. So our y-intercept as an ordered pair is 0, 11 over 4. So then we want to find any x-intercepts. And you find x-intercepts by letting y equal 0. Our equation is written in function notation, so f of x is the same thing as y. We'll set f of x equal to 0. So we have 0 equals negative 1/4 times x minus 1 squared plus 3. I'm going to solve this equation by isolating the square. So I'll subtract 3 on both sides. That gives negative 3 equals negative 1/4 times x minus 1 squared. I'm still trying to isolate this square and everything that it's attached to. I'll multiply by the reciprocal of negative 1/4, and that is negative 4 over 1. So negative 4 over 1 times negative 3, that's 12, equals x minus 1 squared. Now that I've got the squared isolated, I'll get rid of the square by square rooting both sides. The square and the square root cancel each other out, leaving me with x minus 1. And I can, first of all, I want to make sure that I put a plus or minus symbol in front of the square root of 12. We do that every time we square root a square. And we want to simplify that square root of 12. That's going to be 4 times 3. 12 is 4 times 3. Square root of 4 is 2, and the 3 will stay inside the radical. So finally, I'll get x by itself. I'm going to add 1 to both sides, and we have x equals 1 plus or minus 2 square root of 3. So my x-intercepts as ordered pairs are 1 plus 2 square root of 3, comma 0, and 1 minus 2 square root of 3, comma 0. Thank you for checking out my videos. Have a great day.